the basics of reinforcement learning. So title of this course is reinforcement learning, right? But we actually haven't studied any reinforcement learning. So this is the first time we study something about reinforcement learning. So let's see what is reinforcement learning and very basic mathematical model for reinforcement learning, which is Markov decision process. So let's start with the definition. So the definition of reinforcement learning is that a machine learning paradigm where an agent learns to make decisions by performing actions in an environment to maximize cumulative rewards. It looks a little bit complicated, but let's see one by one. So this machine learning paradigm, because it's learning-based one, and this figure shows some pipeline, illustration of reinforcement learning. So we have agent and environment. The agent takes action. So you can think like an agent like robots or some characters in video games, or human, anything that can do something. Anything that can do something. We can see that those kind of things are agent. And environment, there can be many environments, like a physics simulator. Or recent world model. There can be also environment, world model. Or very simplified, or the rules in Go game, right? Or some StarCraft game, right? It is like some environment that we assume our agent is interacting with. And agent takes action A, and then it takes action, and then it makes something different in the environment. It affects the environment, and then something is changed in the environment, and then state. From its name, we can know this is kind of state of environment or state of agent. So because it takes some action, there's something changed in the environment, and then we get updated state, which is the output of action through environment, right? And always the goal of agent is maximizing reward, right? So agent make decision by performing action in the environment to maximize cumulative reward. That is the definition of reinforcement learning. So I guess where the reinforce is like some enhancing. So it's like some enhancing, I'm not sure, enhancing agent, enhancing actions of agent, maybe. So that is the reason why we call this such kind of learning paradigm as a reinforcement learning. And the important thing is that it's based on try and errors. We will see details in later, but it's based on try and errors. Try something, and there can be some errors, and then it get feedback from errors so that it can be enhanced, it can be reinforced from such kind of try and errors. That is some characteristic of reinforcement learning. The agent discovers which action is the highest reward without explicit label or instruction. We will see detail, but that is the very interesting characteristic and very distinctive characteristic of reinforcement learning compared to other learning paradigms like a supervised learning. Supervised learning, we need explicit target, right? We need explicit labels or instruction to compute loss function to optimize something. But reinforcement learning, without explicit labels or instruction, it can be seen like unsupervised learning, but it is also different. We'll see detail. What is the difference between reinforcement learning and supervised learning? What is the difference between reinforcement learning and unsupervised learning? And examples, they're just a typical example, like a lag robot learning to walk by receiving positive reward for forward progress and negative reward for falling. Or robotic arm learning to pick up diverse objects through repeated attempt and feedback on gradual success. Just a typical example of reinforcement learning and some robot learning. So let's revisit supervised learning first. So supervised learning, assume most of you guys know what supervised learning is. Just a very typical learning paradigm in machine learning. Minimize distance between outputs and target. So assuming we have large-scale data sets, and then we have a paired data set of some input X, input, and Y label. And then we have we have a data set. We have data set which consists of input and output, input and label tuples, right? So that let's say we have such kind of large data set, and then supervised learning assumption is that we have such kind of data set that we can train a neural network or optimize something by minimizing distance between output of some system and then targets, right? So requirements of supervised learnings are targets for all inputs in the data set. We need label so that we can compute loss function. And then gradient from loss function is backpropagate to neural network weights, and they are optimized. And another one is that differentiable loss function. That is definitely true, right? We need loss function which are differentiable so that gradient backpropagation can be included in this computational graph. So these are two requirements for supervised learning. Typical machine learning problems like object detection satisfy such requirement, but not in some cases. Some cases, targets for all inputs in the data set might not be available, or loss functions could be non-differentiable. So that in such cases, RL could be useful, right? So let's see. So we talked about two things: data set, data, and loss function. So we will see one by one: data and loss function. So first one is data. So in some cases, data collection is almost infeasible, almost impossible. Let's take an example of some Go or some video games, RTS, StarCraft, such kind of video game, or Go. There can be many combinations of character position and status. You can see from this screenshot that there are many units, right? There are many units, and there can be many possible positions of all units, and there can be many possible combinations of actions for all characters. The possible combination number is too huge, so that we cannot construct all possible combinations of character position, status, action, so that that is the one. Some cases where data collection is almost impossible. And desired user input depends on so many things, including history of play, right? So not only current state, but also history can affect the future actions. So that in such cases, collecting many data set is like, maybe we can, if we have lots of money, we can, but it may be very hard to collect many data sets. It becomes much more harder when we talking about robots, because Go or StarCraft, they are in virtual space, right? They are in screen space. So that if we have good simulator and then we have lots of money, if we have lots of servers, then maybe we can collect lots of data. But the robots, it is so much more difficult. So for all joint rotation and global positions, there are too many desired robot actions. It is the same as the previous example, but the important thing is that robots should move. Robots are moving in real-world physics space, so that to collect physically executable robot data, we need to actually run robots to perform estimated actions from neural network during the training. So what does this mean is that let's say we train some neural network, and then let robot perceive current situation and then do something based on perception, but we need to actually run robots in our real world, right? Not in, to actually make robots to real environment, then we need to run robots in real space, not in simulator, right? But when we run robots in real environment, then many unexpected things could happen. For example, robots could make a collision with some object, and then it can crush some object in our environment, or it can fall and then it breaks like this. Robots are expensive, so broken robots, we need lots of money to fix robots or purchase robots. We need lots of time to fix robots, purchase robots. It's very costly, right? Both time and money, very costly. And there are many things, like if we run robots quite often, then temperature goes high, then something unexpected could happen. When temperature is too high, then a function that robots could do when temperature is not too high, then it can perform some actions, but when temperature goes too high, then it cannot perform some actions. So that there can be many unexpected things of robots when we training robots in our real environment. So that is difference between the previous examples of in screen space and then robots in physics space. That is difference. And small errors in estimated action could make robots broken. When training neural network, the initialized weights might be not optimal, right? That is definitely true. When initializing, although we do some pre-training, the weights of the neural network might be far from optimal weights. But that at the early of the training stage, robots can do very random actions, right? Randomly walking around this area without perceiving properly the environment. In such cases, robots can make collision with surrounding object, and then it can, if it's broken, then as I said, we need to fix it. We need to purchase new robots. They're always very costly. Robots are very expensive. They're very different from the previous example. Another thing is that it's like the robot's action should be physically executable. So robot behavior and RGB videos are both temporal signals, but videos, we have lots of videos on YouTube, right? It's also related to the data set collection difficulty of robots that I introduced you in the first time of this course. So robot behavior and RGB videos are both temporal signals. However, large-scale digitalized robot behavior data is scarce, right? Because YouTube, the capturing video and uploading video to YouTube is very easy. Any people can do that. But capturing robot action and then cleaning such capture robot action and then such kind of process, not everybody can do that. Expert level people can do that. So that the amount of data that we can use for training robot is very limited compared to videos on YouTube or Instagram, social media. So that we have billion scale video on the web, but robot data is very scarce. So that what I was talking about is this one. Targets or for all input in the data set should be available for supervised learning, but robots or some characters in games or some agents, it might be almost impossible to collect data. This is a little bit different story, but these days, many big tech companies are trying to do this. Just use supervised learning, just invest infinite amount of money, and then just collect lots of data using teleoperation or anything. They invest lots of money, and then they make this kind of huge data set for supervised learning. That is VLA, these days VLA. That many big tech companies these days are trying to construct data sets and then just use supervised learning based on the large amount of data sets. Because RL it seems interesting and useful, but in practice it's too slow. It is not scalable. So that is about data. So robot data, usually in practice, if we have some limited budget, both time and money, then collecting lots of robot data is almost impossible. Another thing is loss function, which is the second one that I introduced to here. The requirement of supervised learning was data set and loss function. Collecting robot data is almost impossible for all combinations of robot status. And then loss function. Loss function, for supervised learning, loss function should be differentiable, but unfortunately, robot training, loss function is not differentiable. We make loss function differentiable, but the computational graph many of the computational graph are not differentiable, so we make some tricks to make loss function differentiable. Let's see detail. So during training robot, I didn't introduce policy network, but you can ignore policy. So let's say we have some neural network for robot. During the training robot network, it outputs some robot actions, right? And we need to apply such actions through a physics simulator or real environment, because such kind of action should take physics into account, right? Physics simulator, all physics laws are implemented already, and in real world, also physics laws are already included, right? So that let's say neural network outputs some actions. And then we need to apply such actions through a physics simulator, not simply doing matrix multiplication or such kind of thing. For the physics constraint. Physics constraint mean like a gravity or collision with object or fraction or such many things are happening in physics space, right? All things are implemented in physics simulator. So we need to apply such estimated actions through physics simulator. That means network. Let's say we have some network that S in is a state, input state of robot. S out and S in are output and input state of robot respectively. State means like current position, current velocity, current rotation, anything. You can define any current status of robot as S in, current one. So from current one or some captured images of the surrounding environment, that is observation, and that can be also part of S in. So anyway, the network takes S in and output something, some action, and then we apply that action to the simulator. And then we get updated output, updated state, which is denoted by S out. The problem is that neural network is usually differentiable, but a physics simulator is not differentiable. That is the problem. We need to apply actions in physics simulator or real environment, anything is okay. But such kind of physics simulator or performing something in real environment, they are not differentiable. But we need them. They are necessary for the physics constraint. So how can we do that? Given non-differentiable output function, how can we design loss function to optimize weights in network? The goal is optimizing weights in network, right? So that we need some differentiable loss function, to optimize weight in neural network. But the physics simulator, SIM, is not differentiable. These days, some simulator are introduced, some differentiable simulator are introduced, but even Isaac Sim or Isaac Lab, very recent NVIDIA's physics simulator are not differentiable. So that how can we do that? How can we optimize weights in neural network given non-differentiable output function? That is the second motivation of reinforcement learning. The first one is data, collecting all possible combinations of data. It seems almost impossible. The second one is loss function. We need to apply actions in physics simulator or real-world environment. Those two are not differentiable. So how can we? But we need them for physics constraint. Then how can we do that? How can we optimize weights in neural network? How can we make loss function differentiable? That is the motivation of reinforcement learning. So to summarize, if you are in two situations, like invisible data collection or non-differentiable computational graph because of the physics simulator, then we can try reinforcement learning. Of course, representative examples are agent in video game and robots. Let's say we have some characters in video game, and then we'd like to make a character interact with the world. We cannot collect all amount of data, and the video game, which is included in computational graph, is not differentiable. So that is the motivation of reinforcement learning instead of supervised learning. For supervised learning, we need two things: collected data, differentiable loss function. But in agent in video game or robots, both are not satisfied. Invisible data collection, non-differentiable computational graph. So this shows the very simplified pipeline of reinforcement learning. The neural network outputs action that change the environment state, as I said. So there's a neural network and takes state. State means, as I said, current status, like current position, captured images, or anything of current status. A network takes current status and output action, like move arms in 30 degree or go forward in 1 meter. Such kind of thing could be action. And then it changes the environment, right? It is happening environment. For example, physics simulator. The network outputs some action, and then we apply such kind of action in environment. For example, physics simulator. So here, first problem happens. It is non-differentiable. When we apply such actions in environment, then computational graph is cut, and then gradient cannot be backpropagate in this direction because it is non-differentiable. Anyway, we apply actions in environment, and then we get updated state, right? Like if we, let's say action is to go forward 1 meter, and then the position of robot changes, right? And then we can get updated state, which is in t+1 time, and then reward. So we always have some goal, right? Like for example, we'd like to make our robots reach to that door. Then the reward could be distance between current robot position and the position of that door, right? We can design such heuristic reward that is kind of loss function, different from loss function, but then we can design some reward based on our heuristic or handcrafted implementation. And then a predefined reward function. This is predefined one. Predefined reward function evaluates how desirable the resulting state is, right? So our goal is making robots reach to that door, but with some reason, robots go backward. Robots go like this direction. Then reward could be lower, right? But robots could, in some iteration, network outputs good action, so that robots move to like this direction. Then reward could be high, right? So that it evaluates how desirable resulting state is. This one. The network is encouraged to repeat action that leads to higher reward. And then how can we compute loss function? Here is loss function. We have action from network, and then we have reward from state, right? State from non-differentiable physics simulator. And then we can compute action and reward pair, right? Which action makes higher reward? We can compute such kind of thing after applying actions in environment, right? And then we encourage neural network to repeat action that leads to higher reward. And here, another thing is that there's no explicit target value. Usually in supervised learning, we do not need this one. We do not need this one. We just simply supervise actions with the explicit target action, right? We just simply supervise output of neural network with the explicit target in data set. But as I said, in reinforcement learning, we do not have explicit target value, so that we just encourage neural network to repeat action, which is, this is not a label from data set. This is the output of network. But we compute reward for each action, and then we encourage network to repeat actions that lead to higher reward. That is the philosophy of reinforcement learning. We do not have differentiable environment. We do not have explicit target value. In such cases, even in such situations, we can still optimize weights in neural network with this computational graph. So we will see also these details in later time, but that is the reason why we call this reinforcement learning as a trial and error. At the first slide of this today, I introduced reinforcement learning as a trial and error. That is, trial and error come from this one. So we try some action, right? Try very random action, try many actions in the environment, and then we perform all actions in the environment, and then we get reward for all actions, each action. And then for some actions, it has good reward. For some action, it has bad reward. And then try, and then error is from the reward. And then it pick actions with high reward, and then repeat neural network, encourage to repeat actions that lead to higher reward. That is the try and error. And that is the reason why we need to design neural network in reinforcement learning to encourage exploration. So if neural network outputs neural network output usually have a output distribution of action. But if standard deviation of action is very small, like this one, standard deviation is very small, then neural network will not explore environment, always output some, almost always the same action, so that it cannot try various actions. And then in good cases, all actions could have good reward, and then we can optimize neural network in a good way. But in this case, if standard deviation is very small, and in some bad cases, all actions have bad reward. Then we cannot train neural network because we need to find some actions. We need to let network produce some actions that leads to higher reward. But in bad cases, especially when standard deviation is too small, the network cannot explore environment. Network cannot explore action space, so that we cannot find some actions with higher reward. So that we need to design your network, explore the environment, and try many actions. And there's a trade-off, right? If the distribution is too uniform, standard deviation is too high, like this one. If standard deviation is too high, then we cannot make network converged, right? If we try too many things, then the convergence speed will be too slow. But if the network do almost the same thing, always standard deviation is too small, then it cannot explore environment, so that it might be stuck in local minima. So there's a good, important hyperparameter, standard deviation of the action distribution. So we need to find a good standard deviation which can try lots of actions and at the same time converge fast. That is the important hyperparameter of the network when we do reinforcement learning. We will see this kind of standard deviation things in later. But the important thing in this slide is that the computational graph of reinforcement learning looks like this. The environment, for example, physics simulator, non-differentiable, no explicit target value. Let's see supervised learning. We know supervised learning, right? It is very different from reinforcement learning. The neural network outputs some values, right? It outputs some value, and then directly compute loss function with the output value and corresponding target. This is from data set, right? From data set. So network is encouraged to change output to the target value. This is very different. We know the answer. We know the answer for all inputs, and then we just enforce neural network to produce some output that is close to target, because we have no explicit target and it's fully differentiable, so that we do not need to apply. We do not need to introduce additional environment here, right? We just simply directly compute loss function between output and target instead of passing output to additional environment, right? That is difference. So that is also difference between reinforcement learning and unsupervised learning. Usually unsupervised learning, it is a little bit ambiguous, but unsupervised learning, usually we do not introduce additional environment. Unsupervised, the representative example of unsupervised learning is like self-supervised learning. Self-supervised learning, like it is Dino V2 or this kind of feature extractor trained with the self-supervised learning. Such kind of unsupervised learning algorithms, they do not introduce additional environment. We just compute some loss function directly at the output of the neural network. But reinforcement learning, we need to introduce additional environment for some reasons. In case of robot, we need to introduce physics law, so that we need to introduce additional environment. That is the difference between reinforcement learning and unsupervised learning, reinforcement learning and supervised learning. So, and such kind of thing makes RL a little bit slow, because we need to apply actions in the physics simulator. Physics simulator, it is not very too slow, but it also makes some overhead, right? In the overhead, the computational graph. So reinforcement learning, and this is called rollout. We will see, we also learn later, this is called rollout. Applying actions in the environment, that is called rollout. Rollout takes time in physics simulator. If we use very high-end, very good physics simulator, then it will take more time. If it has very complicated physics interaction, then it will take much time. Anyway, compared to supervised learning or unsupervised learning, the reinforcement learning needs to introduce environment to get updated state, and then such kind of rollout environment makes reinforcement learning slower than supervised learning, unsupervised learning. So in these days, we construct lots of huge scale data sets, right? But how can we train RL systems on such kind of huge scale data set? It is very difficult because, as I said, we need to introduce environment during the training, which makes training too slow. That is the reason why, as I said, big tech companies try to build a targets for all inputs in data set, making VLA. VLA is learned with supervised learning, not reinforcement learning. We will see VLA later. Anyway, so that is difference. Is it correct? Is it clear? Okay. Any question? Go ahead.
So in the physics simulator, is data collection is always impossible, or you just preferably use RL?
So your question is, collecting data in physics simulator is feasible or not? That is your question?
Yeah.
So physics simulator, physics simulator just the environment. So maybe we can collect data in physics simulator, but there can be something like, so first, physics simulator is not a real environment, so that there can be always sim to real gap. So although we collect lots of data in physics simulator, I'm not sure the value of such data set because of course, in some sense, it could be useful, but although we construct large-scale data sets in simulator, still there is a sim to real gap, so that anyway, we will always need a data set in real environment, so that the answer to your question is that yes, we can collect data in simulator, but that might be not enough. We need to still collect more data in real environment to reduce sim to real gap. Any more questions? And let me introduce some examples of RL used in back in the day. Cart pole problem. So objective is like balance a pole on top of a movable car. This is a movable cart. And then state is angle, angular speed, position, horizontal velocity, and action is horizontal force applied on the cart. So neural network take state as an action, right? No, state, input, output, action. So neural network takes this state, output, this action. Reward, we can design reward, and depends on your preference. Maybe one possible reward is 1 at each time step if the pose is upright. So that if we train this network with long iteration, then maybe we can it tries to maximize the reward, right? So that it tries to maximize the time if the pole is upright. And robot locomotion. So it looks a little bit old physics simulator, but physics simulator looks like this. You can see there's a sim to real gap. There is a sim to real gap. Looks very different from real environment, right? So I guess this might be Bujoko maybe. But there are several physics simulators, like Bujoko, Isaac family, or what was that? Genesis. There's a couple of several physics simulator. It looks like Bujoko. The geometry fidelity, the photorealistic rendering capability is very limited. But the physics law is very accurately implemented. So that is the good thing of such kind of physics simulator. Such kind of physics simulator is focused on, from its name, we can know that it is focusing on physics law. But there are many other types of simulator, like for example, video game engine, Unreal Engine, Unreal or Unity, Unity. They have some different characteristics. So Mujoko, Isaac, Genesis, they usually call it physics simulator, but these are some game engine. Because the physics laws in this kind of video game are a little bit loosely defined. So there are some physics failure cases in Unreal and Unity to make them visually pleasant. So the goal of such kind of video game engine is making a visually pleasant rendering. It should, if we focus too much on physics, then the first one is rendering could be too slow. We need to compute all the physics interaction between object and object, so make rendering too slow. And if we focus too much on physics low, then the rendering, the rendering quality might not be good. So for example, if there can be small collision between object and character in Unreal or Unity engine, but if there's such kind of thing happens in physics engine, so this object could fly away because if the collision is too severe, then object could fly away. But such kind of thing could not be happen in video game, so that it compromise physics fidelity while it tries to make the visually pleasant. So this different goal. It is about visual rendering, and this is about physics law. About video generative model. So we can make, this is a little bit different story, but we can make a graph visual fidelity, and visual fidelity, then video generative model, Unreal, and Isaac. Physics, video, Unreal, Isaac. Video generative model, they are focusing on visual fidelity, and they do not have physics law, so that they sometimes produce videos with physics failures, right? But they have good photorealistic generative videos. Unreal is an intermediate thing between video generative model or 3D, typical 3D stuff, intermediate thing between strict physics engine and video generative model. This is strict physics engine. This is a different. This was a different thing. So anyway, let's get back to this example. Objective is make the robot move forward, and state could be angle and position of the joints, and action torque applied on joints, and reward 1 at each time step upright, and forward movement. So we can. This also depends on your design. You can design your network, which state it will take, which action it will output, and which reward function are you going to use. That is depends on your implementation. Or Atari game, very simple video game like this. You complete the game with the highest score. State, raw picks the input of the the game state. Action, game control, left, right, up, down, reward score, increase, decrease at each time step. Also in this situation, in this example, you can design your own state, action, and reward with your preference. And this is goal game, objective window game, state position of all pieces, action, where to put the next piece down, reward 1 if win at the end of the game, 0 otherwise. It was almost 10 years ago, right? 10 years ago, AlphaGo beat Korean player Isador. And at that time, reinforcement learning also used. Reinforcement learning plus, I remember, random forest. Combination of reinforcement and random forest. These days, of course, much more advanced algorithm could be used, but 10 years ago, AlphaGo. It's good? Anything is unclear? And let's proceed to the Markov decision process. So this is the figure that I introduced, which is a kind of illustration of reinforcement learning. We have agent environment. Agent performs some action environment, and it updates some state of that and agent so that we can get updated state, that we can get reward from the updated state, right? That is how we interact with make interaction between agent and environment in RL. And the most simplest mathematical formulation of RL problem is Markov decision process. Markov property is like a current state completely characterizes the state of the world. In many cases, this is not true. There's a very strong assumption to make this RL, this kind of formulation easy. So Markov property is like this one, and then it's defined by 5 things. The first one is S, a set of possible states, A, set of possible actions, R, distribution of reward given state action pair, and P is a transition probability distribution over next state given state action pair, and gamma is discount factor. We will see details. So we covered these three things, and these two are not introduced yet. At time step t equals to 0, environment samples initial state as 0, and then for t until done, agent select action at, environment sample reward, environment sample next state, agent receive reward rt, and next state as t plus 1. This is, exactly the same as this one, right? Exactly the same as this one. Network output, agent use state as an input and then output some action, and then it change some state in the environment, and then we have updated state, then we get reward. Exactly the same as this one. And the policy pi is a function. That is the reason why we call a network a policy network. Most of the R algorithm, the goal is training policy network, a function from S to A, which takes state and output action. That is called policy network. That specify what action to take in each state. An objective is find optimal policy network, pi star, that maximizes cumulative discounted reward. What discounted means, gamma, here gamma, we have gamma, right? Gamma is like usually set to 0.99. Because t, as time goes, it becomes future, so that we have uncertainty at the future state, because we only have observation of the current state, so that we do not know what will happen in future, so that we discount reward for future. That is why we call discounted reward. As time goes, the gamma t becomes smaller and smaller, right? Gamma t becomes smaller and smaller. So as t goes infinite, then gamma goes to 0. So objective is find policy network pi star that maximizes cumulative discounted reward. And this is a simple Markov decision process example, a Greek word. Objective is reach one of the terminate state, like this one, in this number of actions. And set a negative reward for each transition. Random policy might like this one. Just any action you can try. The optimal policy maybe looks like this one, right? Because the goal is to reach to this gray area, so that the optimal policy should look like this. And we want to find the optimal policy pi star that maximizes the sum of reward. And how do we handle the randomness, initial state, transition, probability? We can maximize the expected sum of reward. So formally, we can write like this. In most of our problems, always the goal is finding optimal policy network pi star. Mathematically, we can write like this: argmax pi, expectation of the cumulative discounted reward, right? S0 is from initial state, and AT is pi is a policy network, so that from state, policy network outputs action, and then state, we can, in practice, we can use physics simulator to get updated state, so that we can, the goal is finding optimal policy network pi star, which is mathematically formulated like this: argmax pi, expected sum of discounted reward. And then following a policy produces sample trajectories or path. And then how good is state? We need to decide how good is the state, so that we introduce additional one, a value function, a state S is the expected cumulative reward from following policy from states. It's just it looks like a little bit complicated, but a value function is just a sum of discounted reward, right? Initial state is S, and then just getting some expected cumulative discounted reward. That is the value function. And Q value function is a little bit different from value function. Q value function at state S and A. So value function takes only S state, but Q value function, it takes state and action at the same time. It's the expected cumulative reward from taking action A in state S and then following the policy. I mean, the philosophy is the same, just trying to get to know expected sum of cumulative reward based on current state and current action. It's like a forecasting future, right? Forecasting future. But value function, it only takes state. Q value function takes state and action at the same time. So based on current state and action, it tries to forecast future, so that we can decide how good its state is. If value function is high, then we can say that current state is good. If Q value is high, then current combination of state and action is good. So that we can decide which state is good or which state action pair is good based on value function or Q value function. And then this is called Bellman equation. It's just we can rewrite this kind of mathematical formulation in a recursive way. So the optimal Q value function, Q star is the maximum expected cumulative reward achievable from a given state action pair. This is the same thing that I showed you in previous slide. And Q star satisfies the following Bellman equation. It just just different representation. So if optimal state action value for the next time step, Q star are known, then the optimal strategy is to take action that maximizes expected value of reward plus gamma Q star S prime A prime. I mean, it looks like a little complicated, but I think you can understand this one. This is the same as the definition of Q value function in the previous slide, and then we can rewrite this one mathematically a little bit different, and this is called Bellman equation. So this one is reward, and then if we have the same thing, we can use same thing, and then for the future, then we can rewrite this in a recursive way, like gamma max A prime Q star S prime A prime when S and A are given. That is just the Bellman equation, and this is intuition of Bellman equation. So the optimal policy network pi star correspond to taking the best action in any state is specified by Q star. That is, of course it is true. The optimal policy network correspond to the some network that takes best action in any state as specified by Q. But important thing is that then Q should be accurate, right? What action which we will take is based on Q value, estimated Q value, so that Q value should be accurate. If Q value is accurate, then we can perform good actions. Always perform optimal actions, as long as Q value is accurate. It tries to perform best action in any state, right? Given current RF problem setup, how can we solve the optimal policy? How can we get optimal policy? If we have some limited environment, and if we do not have data, then we can try tabular RL. Where is tabular? Tabular RL. We can make a huge table. It's like a dynamic programming. Do you know dynamic programming? Maybe you learned in algorithm class. We can make a table, right? And then we can fill numbers for each iteration, right? Each iteration. Make a 2D table for all S and A pairs, starting with the initial state, and then fill all numbers in this table. Let's say this is the initial state, and then if you perform some action at the initial state, then we have Q value, maybe 2, maybe 3. And as I increase, then state is changed. At the initial is 1, but the next one, and then we take different actions, maybe this one, and maybe this one, so that as I goes, then we here Qi will converge to Q star as I infinite, right? Because we iteratively update the Q value for all pairs of S and A. So that is the reason why I say if our environment is limited, then we can make this kind of huge table, 2D table for all S and A pairs. And then we can compute this kind of table. We can fill all numbers. And based on if we have this kind of table, then we can perform optimal action for any state. Then we can get optimal policy. That is optimal policy, which can make the expected sum of cumulative reward maximized, right? We can make this kind of 2D table for all S and A pairs. But the problem is that the assumption, the environment is not usually limited. We cannot, not scalable. The problem is not scalable. How can we make this kind of S and A table for StarCraft or robots? There can be many possible states. For each state, there can be many possible actions, especially if we are in continuous space. So that how can we make this kind of 2D table? It is not scalable, right? We can make this kind of S and A tabular RL table. For this example, maybe you can try this one. We can make S and A table with a very limited environment, right? But when we talking about robots, when we're talking about robots, then there are too many possible states, too many possible actions, so that we cannot pre-compute such kind of table for all possible combination of S and A. So solution is, so that's not scalable. Must compute Q S and A for every state action pair. If state is current game state pixels, computation is infeasible compared for entire state space. Solution is use a function approximate to estimate Q and A. So that instead of making huge table, we can introduce a neural network that takes S and A as a inputs and outputs Q value. That is the deep Q network. Deep Q network. Using deep network, we can design a network that takes S and A, outputs Q value, which we will learn in next class. So that is the motivation of deep Q network. To get optimal policy in a little bit traditional RL, we need Q value, but it is in many cases it is not computationally feasible. So that alternatively, we can introduce network that takes S and A and outputs Q value, which is called deep Q network. Okay, let's finish today. Any question? Okay, let's finish. Thank you.